In number theory, a cyclotomic field is a number field obtained by adjoining a complex primitive root of unity to Q, the field of rational numbers. The nth cyclotomic field Q is obtained by adjoining a primitive nth root of unity zeta n to the rational numbers. The cyclotomic fields played a crucial role in the development of modern algebra and number theory because of their relation with Fermat's last theorem. It was in the process of his deep investigations of the arithmetic of these fields, and more precisely, because of the failure of unique factorization in their rings of integers, that Ernst Kummer first introduced the concept of an ideal number and proved his celebrated congruences properties. A cyclotomic field is the splitting field of the cyclotomic polynomial, and therefore it is a Galois extension of the field of rational numbers. The degree of the extension, Q, is given by phi, where phi is Euler's phi function. A complete set of Galois conjugates is given by A, where A runs over the set of invertible residues modulo n. The Galois group is naturally isomorphic to the multiplicative group times of invertible residues modulo n, and it acts on the primitive nth roots of unity by the formula B, AB. Relation with regular polygons. Gauss made early inroads in the theory of cyclotomic fields, in connection with the geometrical problem of constructing a regular n-gon with a compass and straight edge. His surprising result that had escaped his predecessors was that a regular heptadecagon could be constructed. More generally, if P is a prime number, then a regular p-gon can be constructed if and only if P is a Fermat prime. In other words, if is a power of 2. For n equals 3 and n equals 6, primitive roots of unity admit a simple expression via square root of 3, namely, zeta 3 equals square root 3i minus 1/2, zeta 6 equals square root 3i plus 1/2. Hence, both corresponding cyclotomic fields are identical to the quadratic field Q. In the case of zeta 4 equals I equals square root minus 1, the identity of Q to a quadratic field is even more obvious. This is not the case for n equals 5 though, because expressing roots of unity requires square roots of quadratic integers. That means that roots belong to a second iteration of quadratic extension. The geometric problem for a general n can be reduced to the following question in Galois theory. Can the nth cyclotomic field be built as a sequence of quadratic extensions? Relation with Fermat's last theorem. A natural approach to proving Fermat's last theorem is to factor the binomial xn plus yn, where n is an odd prime, appearing in one side of Fermat's equation xn plus yn equals zinc as follows. Xn plus yn equals. Here x and y are ordinary integers, whereas the factors are algebraic integers in the cyclotomic field Q. If unique factorization of algebraic integers were true, then it could have been used to rule out the existence of non-trivial solutions to Fermat's equation. Several attempts to tackle Fermat's last theorem proceeded along these lines, and both Fermat's proof for n equals 4 and Euler's proof for n equals 3 can be recast in these terms. Unfortunately, the unique factorization failed in general. For example, for n equals 23, but Kummer found a way around this difficulty. He introduced a replacement for the prime numbers in the cyclotomic field Q, expressed the failure of unique factorization quantitatively via the class number Hp, and proved that if Hp is not divisible by P, then Fermat's theorem is true for the exponent n equals P. Furthermore, he gave a criterion to determine which primes are regular, and using it, established Fermat's theorem for all prime exponents p less than 100, with the exception of the irregular primes 37, 59, and 67. Kummer's work on the congruences for the class numbers of cyclotomic fields was generalized in the 20th century by Iwasawa in Iwasawa-Theorion, by Kubota and Leopold in their theory of p-adic zeta functions.